Welcome. This is Coach Dorf. We're going to talk about section 1.4, which deals with exponential functions. So let's look at the laws of exponents. So there are four main laws here. The first one is that if you have a base to the x power and you have that same base to the y power and you multiply these together, then you can go ahead and write the base and add the exponents. So for example, if I have 2 to the 5th times 2 to the 3rd, that's going to equal 2 to the 8th. The second exponential law is if I divide these, then I'm going to subtract the exponents. So an example of this would be, suppose you had x to the 3rd over x to the negative 2. Well, that's going to equal x to the 3rd minus a negative 2, which is going to be x to the 5th. The third law is if you have a base to a power and all that's to a power, you go ahead and multiply the two powers together. So an example of that could be if I had 3 to the 2nd power all to the negative 1, that would be 3 to the negative 2 power. And now anytime you have a negative power, that's the same thing as writing 1 over that to a positive power. And the fourth and last property that we'll talk about is if I have a base and two bases, like a and b, and they're to a power, then that's going to be a to the x, b to the x. All right? And an example of that could be if I had 2 xy to the 3rd power, and that's going to be 2 to the 3rd, x to the 3rd, y to the 3rd. Okay, so let's do some examples of this here. So the first example here is we're going to simplify the following. We have 2x squared y over the quantity 3x to the negative 2 y all to the 2nd power. So when I simplify that, I'm going to use the laws or properties that we had up above. So the first one I'm going to do is I'm going to start at the bottom denominator, and I'm going to use this 2 here, and I'm going to use property 4, okay, which says that I can distribute this negative 2 to everything, or this positive 2 to everything. So I'm going to have 2x squared y on the top, and on the bottom I'm going to have 3 squared x. Now I'm multiplying a negative 2 times a 2 because the 2 is outside, I'm also using property number 3 here. So when I multiply the 2 by the negative 2, that gives me a negative 4, and then I have y to the 2nd power. Now I'm going to use property number 2 here, so property number 2, and I'm going to get 2, and now I have an x here on the numerator. I have an x squared, and the bottom I have an x to the negative 4th, so I'm going to have 2 minus a negative 4, and then and I have y. There's not a number next to the y, so that means it's a 1, and so I'm going to have a 1 minus 2 on the y power. And in the denominator, I've got a 3 squared, which is 9. So I could write this as 2/9 x to the 6th, because 2 minus a negative 4 is 2 plus 4, which is 6, and y to the negative 1. and then I would finish that by just writing this as 2/9 x to the 6th in the top, and because I have a y to the -1 in the top, I can bring that into the denominator and write it as y to the first power, or just y. Okay, that was the first example. Let's look at a second example. Simplify. Here we're going to look at 27 to the 2/3 power. So what does it mean to be to the 2/3 power? Well, I'm going to use one of those properties of exponentials. So I'm going to write 27 here, and I'm going to separate the 2/3. I'm going to first do the 1/3, and then outside of it I'm going to put the 2. Okay, so this is like using property number 3 here, except backwards. Okay, because property number 3 would say if I had 27 to the 1/3 all to the squared power, I'd multiply the 1/3 by the 2 to get 2/3, which is what I started with. Now, why do I do that? Well, what does a fractional power represent? It is like a root of the number. So 27 to the 1/3 is the same thing as 27 to the cube root, or the cube root of 27, and then it's all to the second power. And what does a cube root mean? Well, a square root, so the square root of 16 would mean what number times itself equals 16. The cube root means what number times itself 3 times equals 27. So what number times itself 3 times equals 27? That would be 3. And then I have a square, and then 3 squared is 9. In a problem like this, where you started off with 27 to the 2/3, you could have done 27 squared and then taken the cube root of it. So you could have done 27 to the 2/3 equals 27 squared, all to the 1/3 power. Okay, but that's really complicated. 27 squared, okay, I'd have to figure out what that is, and then I'd have to figure out what number times itself 3 times equals that 27 squared. I find that it's much easier to do the denominator part first when you have a fractional exponent. So I will always do that. So in this case, it's easier to do the way I did it by doing the 1/3 power first, 27 to the 1/3, and then squaring it at the end. Okay, and let's do one last example. Suppose I had -2 to the 6th over 4 cubed. And I want to find the solution to that. Okay, so first of all, let's talk about this. What does -2 to the 6th mean? Does that mean -2 times -2 times -2 6 times? So is that -2 times -2 times -2 4 times, 5 times, 6 times? Actually, it does not. It doesn't mean that. Okay, instead, get some more colors in here. -2 to the 6th means -2 times 2 times 2 times 2 times 2 times 2. Okay, that negative is outside of the 2 to the 6th. So you do to the 2 to the 6th first, and then you put the negative. So you may ask, well, what if I wanted to do -2 times -2 times -2 6 times? Well, in that case, you would write -2 to the 6th. So notice that -2 to the 6th would be -2 times -2 times -2, -2, another -2, and another -2. So -2 to the 6th is not the same thing as quantity -2 all to the 6th. They're different numbers. All right, so let's go back to the original problem. We had -2 to the 6th over 4 cubed. Now, I can't apply the exponential properties here because I have different bases. I have a 2 on the top and a 4 in the denominator. So what I would do in this case is I would change the bottom so that has a base of 2. And how can I do that? Well, 4 is 2 squared. So I'm going to have 2 squared everything cubed in the denominator, and then the negative of 2 to the 6th in the numerator. And then if I simplify this, in the bottom, we're going to use property number 3. Since I have a power to a power there, I'm going to have 2 to the 6th, and in the top I have 2 to the 6th. Well, the 2 to the 6th and the 2 to the 6th reduce out, and I just get -1 as my answer. Now some people may say, well, could I have done it this way? Could I have said -2 to the 6th over 4 cubed and just multiply this out? What is 2 to the 6th? 2 times 2 times 2 times 2 times 2 times 2. So I have 2 times itself 6 times. All right, that's 64, and I have a negative in front of it. And what is 4 cubed? That's 4 times 4 times 4 is also 64. And if I reduce that, I get -1. So you get the correct answer that way. You can do it either way. I like to show the first way because that's going to be more common type of way to solve problems, and sometimes it's not as nice as the second way. The second way is very nice in this problem because all the numbers work out evenly, but sometimes they won't, and that way the first approach I did works out well. Okay, so let's now talk a little bit more about exponents. We're going to talk about a thing called the exponential function. So this is going to be a function that looks like f of x equals a to the x power. And what does the graph of that look like? Well, if a is greater than 1, the graph of it's going to look like this. And this point right here is the point 0, 1. In other words, and that's because that would be saying a to the 0 equals what and equals 1. So x is 0, and because this is x equals 0, and the y value is 1 because anything, if a is greater than 1, then a to the 0 is going to equal 1. On the other hand, we can have a function that looks like this. If a is between 0 and 1, we're going to get this. And in this case, we have the function going a different way. So it's kind of like a reflection across the y-axis here. The red and the green are reflections of each other. And they change because of the value of a. If a is greater than 1, we get the green function. If a is between 0 and 1, we get the red function. Notice that a couple things. Notice here in all these cases that a to the x is always greater than 0. All right, that means that the green and in the red graph, it's always above the x-axis. And second thing, notice that we don't have cases where a is less than 0. We're always dealing when a is either between 0 and 1 or a is larger than 1. You may ask yourself, what happens when a equals 1? Well, when a equals 1, then you have 1 to some power, and it's always equal to 1, so you get a straight flat line. Now, in calculus, we're going to talk a lot about a certain number, and that number is the number e, which is approximately equal to 2.71828, and it goes on forever. Just like pi is a number, and that's 3.14159, and it goes on forever. E is another number, and it goes on forever, and its value is approximately 2.7. And so you may ask yourself, where does this e come from? Pi comes up when we do deal with things related to circles, and there's always the common joke that you could have pizza pie or apple pie using the pi symbol there. By the way, there is an International Pi Day, okay, for the math symbol, and that is on March 14th. And I'll let you figure out where that date comes from for March 14th. But what about E? Well, we use this because we're going to be looking at, in calculus, we'll be often interested in this type of expression. Suppose I had y equals 2 to the x. So what does the graph of that look like? Well, it's like the graph of a to the x, but a is 2 in this case. And when a is greater than 1, it was that green graph above, and it looks like this. What I'm interested in is at this point here, if I were to draw a tangent line, and a tangent line is a straight line that intersects at that point there, but it's kind of like balancing on that point on the purple line. So it doesn't intersect the purple line any more than once near that point that we just did here, which is the point, of course, 0, 1, as we mentioned up above. And if I did that, what is that slope of that line? Well, it turns out that the slope of this line is about 0.7. Now, on the other hand, if I were to do the same type of thing, but let's pick a different function, let's do y equals 3 to the x, it's going to look similar, but it'll be a little different here. And this time I want to look at this point, 0, 1, and I want to find the slope of this tangent line. It turns out if my a value is 3 in this case, the slope is about 1.1. And so there's going to be some a value. There's some a that's, let me write it this way. There is some a value where a is between 2 and 3, such that if I looked at the graph and I took that function here, so this is y equals a to the x, and again I'm going to look at that point here, 0, 1, and I look at the slope of that tangent line. That slope is going to equal 1. There's going to be some a value that does that. What a value does this? We know that it's between 2 and 3 because when a is equal to 2, the slope is 0.7, and when a is equal to 3, the slope is 1.1. So it's got to be somewhere between 2 and 3, and the a that does this is e, which is, like I said earlier, is about 2 point, let me look it up here, 2.71828, going on forever. So that's how E comes into this. And we will see E a lot in calculus. It'll be very common. You'll get used to it. All right, so let me give you an example of a function then. So I could have the function y equals e to the x. So e again is just a number here, just like pi is a number. What would the graph of this look like? Well, it's like what we did earlier, where I have a number, a is a base, and that base is larger than 1, so the graph of it's going to look like this. That's what the graph of it looks like. And we're going to use this fact then so we can do some example problems. So here's an example. We want to sketch the graph of y equals e to the x minus 1 plus 2. All right, so going from what we talked about earlier in the first section of this course, this is where we're doing a transformations of the graph. So I've got two things happening here. I've got a plus 2 and I've got x to the minus 1. All right. What does x to the minus 1 do? That moves the graph um, to the right one space. So if I have my graph here, if I'm just going to look at y equals e to the x minus 1, it's going to look like, I'm going to move this all one space over. So now, instead of crossing here at 0, 1, it's going to cross here. So up above, this was 0, 1. This now is going to cross at the point 1, 1. And it's going to look like that. That's what the graph e to the x minus 1 looks like. Now I want to do the plus 2. What does the plus 2 do? So I'm going to look at y equals e to the x minus 1 plus 2. So I'm taking my previous function here. And this plus 2, all right, moves it up 2. So I'm going to take my red graph from here, where I had this point here was 1, 1. I'm going to move it up 2, so I'm going to get this point here 1, 3, and my graph now is going to look like that. So y equals e to the x minus 1 plus 2 shifts it to the right 1 and then up 2. Now if you want more examples of this, there's another example. So another example of this in the extra help videos that are on Canvas in the module. And this is the one like homework number 2. So if you want some extra help on this type of concept, look at that video. It goes through and explains how to do this in a little bit more depth. All right. Likewise, what is homework? This is homework number 2. What's homework number 1? Homework number 1 is like the initial problems we did where we used those laws of exponents. So you can go back to either of those videos if you need some extra help with the homework, or if you want to just check it and look at some more things. All right. Let's do some applications here. So we're going to do an example. And this is similar to one that you will see in your homework. Suppose I have a function that's an exponential function, and I'm going to have it's some constant times a to the x. And suppose this contains, this graph of this function contains the points -1, 3 and the point 1, 4/3. And you're supposed to determine the values of C and A. So in other words, what C and A can I put in for this function so that it would contain those 2 points? Now it might be helpful here to just kind of like look at where these 2 points are. The point -1, 3 is right here. There's the point -1, 3. And if I look at the point 1, 4/3, it's about here. That's the point 1, 4/3. And so if I were to graph that, it looks something like this. And that is an exponential function. If you go back to the original functions, let's look back here a little bit. All right, what did we notice? Which one does it look like? The green one or the red one? It looks like the red one. So I know that A is going to be somewhere between 0 and 1 because that's what happens in the red one. So we know A is going to be between 0 and 1. But we don't know the exact value yet. So how do I go ahead and solve this problem? Well, I'm just going to take the points and plug them into the equation. So for the point -1, 3, I'm going to use f of -1 equals C A to the -1, and that's supposed to all equal 3. All right, I've taken the the negative 1. I put that in for x in those two places, and I end up with 3, so that all has to equal 3. I can do that for the other point, for the point 1 4/3. Then I get f of 1, so that equals c a to the 1 power, and that's supposed to equal 4/3. So I've got these two equations here. Let me rewrite them down here. So I have c a to the negative 1 equals 3, and I have c a to the 1 equals 4/3. Well, let's get rid of this a to the negative 1 here. How can I do that? Well, that's the same thing. Anything to a negative power is like 1 over that. So this is the same thing as c 1 over a equals 3. And then from the one below it, I have c times a equals 4/3. How can I progress from here? What can I do? I've got these two equations. I want to figure out what a is and what c is. All right. Well, let's solve for c. So we're going to solve for c. Solve these equations for c. And that means we're going to get c by itself. So c times 1 over a equals 3. I want to get rid of the a on the left. So I do that by multiplying both sides by a. Okay, when I do that, I get a times c times 1 over a. These cancel each other out here. And I get c, and on the right side I get 3a. So c times 1 over a equals 3 is the same thing as c equals 3a. On the other hand, if I go ahead and I solve the second equation for c, so I have c times a equals 4/3. I'm going to divide both sides by a. Okay, and when I do that, I get c on the left side, and now I have 4/3 over a, which is the same thing. I can write that as 4/3 divided by a over 1, which is the same thing as multiplying by the reciprocal. So I have 4/3 times 1 over a, or 4 over 3a. I think a better way to do that, if you started off with c times a equals 4/3, is to go ahead and multiply both sides by 1 over a. And when you do that, the 1 over a and the a cancels out on the left side, and you get c. And on the right side, you get 4 times 1 over 3a. You get the same thing, but I think it just comes quicker. So now I have two expressions for c equals 3a and c equals 4 over 3a. So I can set those equal to each other. So I have 3a equals 4 over 3a. And now if I cross multiply, so I have a 1 on the denominator on the left side. When I cross multiply, that means I take 3a on the left and I multiply it by the 3a on the right that's in the denominator, and that equals the 4 on the numerator on the right times the 1 in the denominator. That gives me on the left side 3 times 3, which is 9, and a times a, which is squared, equals 4. Divide by 9, I get a squared equals 4/9. Taking the square root of both sides, a equals the square root of 4/9, which is going to be plus or minus 2/3. But in this case, I know that my answer is just positive 2/3, because whenever we are dealing with these exponentials, I mentioned earlier that a can never be a negative number. A has got to be either between 0 and 1 or larger than 1. It can't be a negative, so we have that a is 2/3. How can we figure out what c is? Well, c is going to equal 3 times a. So now I put in 3 times my a value, which is 2/3. 3 times 2/3, so I put a 1 below the 3. Now I just multiply the tops together. I get 6, 3 times 2, and on the bottom I get 3, and that reduces to 2, so c equals 2. All right, so those are my two answers. A is 2/3 and c is equal to 2. Let me do one last example of something here. Okay, and this one here we have things that can grow exponentially. So you've heard about exponential growth. Um, Organisms can grow exponentially. There's radioactive decay, so some radioactive substances decrease in an exponential way. Uh, Money and loans and interest on debt, they grow exponentially usually. All right. You have to be careful though. Sometimes people overuse this and they say, "Oh, this is growing exponentially," when it's actually not. But here's an example of an exponential growth problem. So if we have an organism, we call it in this case, it's going to be a bacteria. So a certain bacteria population doubles every 3 hours. Okay, if there are initially 100 bacteria, then how many bacteria are there after 3 hours? Well, it doubles every 3 hours. So if we start with 100, so we start with 100, After 3 hours, that doubles. What's doubling of 100 is 200. So after 3 hours, 100 doubles to 200. So there are 200 bacteria. All right. How many bacteria? So let me ask you this one. Well, how many bacteria would there be after 6 hours? Well, it doubles every 3 hours. So at the very beginning, there's 100. 3 hours later, there's 200. 6 hours is another 3 hours later, so the 200 doubles to be 400. What if we did something that was in between there? Like what if we did 2 hours? Or how many bacteria would there be at 4 hours? This is a little bit more complicated. And so we're going to do a general case. How many bacteria after t hours? So t is just any time. So in order to do this, we're going to use the formula y. Let me write this here. We're going to use the formula y equals c a to the bt, where c equals the initial amount, all right, a equals the rate of growth, b equals how much a growth happens in 1 hour, and t equals time in hours. So for this problem, what do we know? Well, the initial amount is 100, because we start off with 100 bacteria. A is the rate of growth. Well, we know it doubles every t hours, so A is going to equal 2. Okay, so this is doubling. The tricky part now is to figure out what B is. All right, so what is B? All right, we know that it doubles every 3 hours. So that means that there is one doubling in, so it's one doubling in 3 hours, which is equivalent to saying in 1 hour there is 1/3 doubling. So that means we're gonna say B is 1/3. All right. So it's 1/3 of a doubling in 1 hour. So the equation becomes, so the equation is, remember it was like y equals c a to the bt. So now I substitute those in, I get y equals 100 times 2 to the 1/3 t. That becomes my equation. So now if I put in t equals 3, so notice if t equals 3, what do we get? We have y equals 100 times 2 to the 1/3 times 3 power. So that's 100 times 2 to the first power, or we get 100 times 2, which is 200, right? And which is what we got after 3 hours, okay, 3 being this t equals 3, we have 200 bacteria. But we can also solve that if t is 2 hours, then we get y equals 100 times 2 to the 1/3 times 2 power, which is 100 times 2 to the 2/3 power. And now if I use the calculator, I can figure out what 2 to the 2/3 power is, find that number, and multiply it by 100. 2 to the 2/3 is going to be somewhere between 1 and 2. And I don't know what that number is right off the top of my head, but I can figure out that. And so I'm going to get some number that's between 1 and 2. I multiply that by 100, and I'm going to get then the amount of bacteria is going to be somewhere between 100 and 200, which would make sense. All right. Hope that helps you with this section.